is my topic today, membranes for separating molecules, where we are and where are we going, because I wanted to tell you a bit about current membrane technology for molecular separations, and then go on to tell you about some of the research we're doing at Imperial College in a couple of areas which I find interesting. So I'll first of all talk to you about molecular separations by membranes, and I'll try and explain to you why I think molecular separations by membranes are important and why they hold the key, or they hold one of the keys to reducing the amount of energy that we use in our society. Then I want to give you a bit of a tutorial about making membranes and modules, how they're made, what they look like, and then to touch on a couple of application areas. One of them, reverse osmosis for desalination, the work that Sheetal has alluded to that we've been doing with BP. I'll cover in that part of the talk. And then the other topic, an area which I've worked on for the last decade or so, which is nanofiltration in organic liquids, and then to finish by giving you a little bit of an outlook on the future and what I think the future holds for membrane separations. So if I just touch on what I mean by membranes when I'm talking about molecular separations, obviously membranes can be used to separate out molecules across a range of sizes. So if you go to the largest thing we might think about filtering with membranes, it can be upward of 1 micron, things like, for example, bacteria. But what we're really interested in is down at this end of the scale, when we have molecules which are typically 1,000 times smaller than that. So 1 nanometer, 10 angstroms, or, for example, in the case of salt, even less than nanometers. So sodium is 3.7 angstroms. So typically the sorts of pore sizes that we would need in a membrane for molecular separation is in the range an angstrom to 2 to 3 nanometers. So when I talk about molecular separations in this area here, I'm talking about things like ultrafiltration at the very tight end, nanofiltration, and reverse osmosis. And we're talking about removing things that are dissolved in a liquid or separating molecules in a gas. The most common driving force for these operations is pressure. So what we'll typically do is have a membrane, and we will apply a pressure across that membrane, and depending on the pore size in that membrane, some molecules will be able to permeate through it, and some molecules won't, and so we'll achieve separation of those molecules. Just to give you a feel for the importance of this topic, I want to share with you some information on the energy consumption in the United States. So the American Institute for Chemical Engineers estimate that molecular separation processes, the kinds of things that I've been talking about, account for between 40 to 70% of the energy costs in industry. And if you look at the US data on energy consumption in the US economy, and we divide that into residential, commercial, transportation, and industrial, you can see from this plot on the left-hand side that industrial use is the largest sector for energy use in the US. And about half of the energy used in industry is used in separation processes. And of those separation processes, you can see that something like half of that amount of energy is used in distillation, and another big chunk, 11%, is used in evaporation. And you can see then that evaporating liquids, whether it's in distillation or direct evaporation, is accounting for something like 10 to 15% of the total US energy consumption. Why? It's because when you evaporate liquids, you need to separate the molecules in the liquid. And separating the molecules in the liquid takes quite a lot of energy. And what I want to do now is just to go to a pre-recorded video that explains to you why that is. A demonstration using this equipment here of why membrane technology is so far superior to thermal technology when it comes to purifying water. What I have is 2 bicycles. And on this side I have a bicycle which I'm going to sit on, and when I ride that bicycle, what I'm going to do now is to give you a demonstration using this equipment here of why membrane technology is so far superior to thermal technology when it comes to purifying water. What I have is 2 bicycles. And on this side I have a bicycle which I'm going to sit on, and when I ride that bicycle, the energy I put into riding the bike is converted to electricity in a generator here. And in this case, that electricity is going to be used to heat a coil. And that coil is like the coil that you have in your kettle when you boil water. So as I ride the bicycle, the energy that I produce, we convert it to electricity and use to provide heat to this kettle where the water will boil, the water will come off, it'll go through a coil where it cools down, and purified water will be collected in this cylinder. So you'll be able to see as I ride the bicycle that I produce energy and that I boil water using the energy that I can produce. So let me just get this one warmed up, get it going up to speed. And once I get it up to speed, you can see here's the amount of energy I'm generating. Then the water starts to boil and I recover water. So if I bike and I think I'm not as fit as I maybe should be, I'm starting to get a little bit breathless. I'm going to time myself for one minute shortly as I bike and I produce this energy. This energy is being converted to electricity and boiling the water. You can probably tell that I'm starting to get a little bit short of breath. I'm into my minute now. So I'm going to bike for 1 minute and see how much water I can produce. So all of the output of my biking now has been converted into electricity. That's being used to heat the water, boiling the water, and I'm about 30 seconds through now. You can see I haven't produced a lot of water yet. This distillation, evaporation business takes a lot of water. Oh, well, someone needs to invent membrane technology. This is just no good. No wonder the caveman was so fit. I'm coming up now, 45 seconds. I've got my first drop of water after 45 seconds. And I've had to go up to over 200 watts. And I can tell you I'm feeling it. So I've got about 5 seconds to go. I might have to take a breather after I finish this. Here I come up to my minute. Whew. So that's how much energy it takes to produce a few drops of water using evaporation. Now, that's where we have technology. So on this equipment here, what I have is another bicycle. And I'm going to sit on this bicycle, and again I'm going to pedal. And as I pedal, the energy that I generate is going to be converted to electricity. And that electricity will now drive a pump. So I'm going to use a pump, and that pump will come from the tank, and it will go to a membrane module, which is this unit here. That's my membrane module, and here's my pump. So as I cycle, I'll produce water here. And that water will be fresh water, the same as the water as I was producing from distillation. I think I've got my breath back now. So I'll get this bike up to speed. And here I think I'm going to go more gently and just go for something like 50 watts. A man of my age has to watch how much energy they generate. So if I start now, this is my 1 minute period. Stately cruising along, I can ride no hands even when you have a membrane. And I'm producing 50 watts. And you can see the water coming through into the collection vessel. Starting to fill up, the water's coming through, and you can see with just 50 watts, the rate of water coming through is much higher. I'm 30 seconds in. I do have to say this is much more pleasant riding along with the membrane at 50 watts. You can see the water starting to come through and building up. And the point is that with a lot less energy, and the energy source has been the same in both experiments, the energy source is me, and I had more energy when I started that experiment than I do now, after biking flat out for a minute. I'm producing less power. I'm only producing 50 watts. I'm really generating a lot more water. My last second, that's the membrane bike. Now let's compare how much water I've generated through the evaporation with how much water I've generated through the distillation. Well, here's the evaporation water, and this is rather a small quantity. So you put it into a cylinder. And what you can see here, if you read the gradations on the side of that cylinder, is that I produced about 2 mils of water in a minute of really cycling hard, producing 250 watts of energy. Here you can see the membrane rig. Here I'm going to lift this up, and put the water into this measuring cylinder so we can see it more clearly. In the membrane experiment, I've generated over 50 mils of water. So what a comparison. Here, cycling for a minute at 250 watts, wearing myself out, I've produced 2 mils of water. Here, cycling for a minute, running at only 50 watts, very sedately, I've produced over 50 mils of water. And that is why membrane technology is far more effective than thermal techniques purifying water. Thank you. So you can see that using membranes, you can, with a lot less energy, purify water. And I just want to take you through why that is in terms of the numbers. If you think about what I did, I was just using an evaporator to produce heat, which was used to evaporate water and then condense that water. And so if I consider a meter cubed of water, and I say that I want to, it's got salt in it, so I'd like to evaporate it and then condense it to recover it as pure water, then if I want to do that, I'm going to have to heat it up. And you can see an amount of heat here, 264 megajoules required to heat it up. And then we're going to have to vaporize it. And that takes me 1,980 megajoules. And if I put both of those together and I spend 2,244 megajoules, I can evaporate and then condense 900 liters or 0.9 meters cubed of water. So that's a lot of energy. If I sit on a bicycle and use a membrane, and then it drives a pump, and I put pump energy in the form of electricity, and then I have to run at a pressure drop of 30 bar, if I move the same amount of water through the membrane, 900 liters or 0.9 cubic meters, that takes 3 megajoules. So that's something like nearly 3 orders of magnitude less energy to produce the same amount of purified water using a membrane than it would take me by using evaporation. And that's why membrane technology is far more effective than evaporation for purifying organic liquids and for doing things where you need to separate a volatile organic liquid from other solutes. So to do that, of course, we need membranes. And what I want to tell you a bit about now is making membranes and modules. There's 2 types of membranes that we use. The first type is made out of one material here on top of a non-woven. We call this an integrally skinned asymmetric membrane. So the point is the open part of the membrane here and the more closed tight part of the membrane that carries out the filtration here are all made of the same material. Then the other type of membrane is what we call a thin film composite, because it has a thin film separating layer on top of a more open membrane material down here. So we make an open membrane and then we coat it. So just a bit about how we do each of those, starting with this integrally skinned membrane. This video shows you membrane casting on a benchtop casting machine. So we start with this, what we call dope material. It's about the consistency of honey, so it's a brown solution. It looks like honey. What it really is a polymer dissolved in a solvent. For example, DMF or DMSO or solvent like that, which will dissolve the polymer. We make this thick, gooey dope, and then we cast it to a fixed height on top of a non-woven backing, which is like a piece of paper, and then we dip it in water. And when we dip it in water, the solvent comes out of that polymer solution, and the polymer precipitates on top of the non-woven, and we get a membrane that looks something like this. So what you can see here is the very top separating layer of membrane made from this polymer, which is a polyimide, made up of these 2 polyimides. When we do this phase inversion process, the very top layer of the membrane has these finely divided clumps of polymer. And it's the gaps between these clumps of polymer that gives us pores and allows us to separate molecules. Through most of the thickness of the membrane, it's far more open. So we get a very open structure which doesn't provide much resistance to flow. So that's asymmetric, thick at the top and much more open at the bottom, and we can use that to filter liquids and remove molecules from them. But the other type of membrane, the thin film composite, is a bit more complicated. So we have to start off by carrying out the same process of phase inversion, but now to make a more open support membrane. And then on top of that open support membrane, we carry out a reaction which gives us a very thin film. And typically this reaction is between an aqueous amine solution and an acid chloride in an organic solution. So typically we'll use metaphenylene or MPD and trimethyl chloride. These are the 2 most common ingredients of reverse osmosis membranes, and this one is present in the organic phase and this is present in an aqueous phase, and they react together to give us this networked polyamide layer here. And so the way we do that is we start off with this open porous support, and we impregnate it with the aqueous solution of the amine, and we then contact that with the organic solution of the trimethyl chloride. And they react together to give us this polyamide layer, a very thin layer at the surface of the membrane, and it's that polyamide layer that provides the selectivity. For example, in reverse osmosis, that doesn't let salt pass through the membrane, but will allow water to pass through the membrane. So we have two different ways of making membranes. One step where we do it with phase inversion to make an integrally skinned asymmetric membrane, and then a multiple step process where we put thin films on the membrane. But whichever way we make the membranes, what we end up with is big rolls, like rolls of paper. And we need to then use these to make membrane modules. And the most common way we do that is using what we call a spiral wound membrane module. So you can see here a perforated central tube, and what we're going to do is to wrap leaves of membrane around that perforated central tube. Now it's quite hard to see how those things actually work, so I'm going to show you with the aid of this video how the spiral wound membrane module works. The feed solution actually flows in to the membrane module, and it flows down between the leaves of the membrane. So that comes out as a concentrate. The purified liquid, for example water, if you're desalinating salt water, comes out through the central permeate tube. And so the way that works, if you look into that module, is we had a series of leaves. And in each of these leaves we have a permeate. This is the membrane here, and then this is what we call permeate side or permeate collection. And that flows down and into that central permeate tube. So to construct that, what we do is we take a whole series of membrane leaves, and each one of these membrane leaves is hollow. So it's a membrane on both sides. So what you've got is a permeate spacer, and you've got a membrane on each side of that, so that each one of these leaves has a membrane, then a permeate spacer, and then a membrane. So as fluid pushes down into this membrane, it goes through the membrane, it will then pass down through this permeate spacer until it reaches this perforated permeate tube here in the center. When we wrap that up, of course, we don't want the feed side of the membrane to touch, one membrane to touch the other, because if this membrane touches this membrane, there won't be any room for flow. So what we do is we add a thing called a feed spacer that holds these different leaves apart and stops them from crushing together and allows flow to pass down the module. So in terms of fluid dynamics, when we pass flow through the membrane module, we're typically feeding a flow in this direction, and that flow is then passing into the permeate side of the membrane leaf, going into the permeate tube and flowing out the permeate tube. So you can imagine it as a Swiss roll, where the process fluid is passing down where the jam goes in the Swiss roll. The fluid that you are collecting, the permeate, is going into inside of the sponge and coming around to the middle of the Swiss roll and flowing out. So this is the most common type of membrane module that is used in liquid separations. So what we do when we have these membrane modules is we take them and we put them into what we call membrane housings. So a typical membrane plant will have a few key components. One is a high pressure pump. You'll need a pump using electrical energy to push the fluid up to the operating pressure, a back pressure valve that holds the pressure on the membrane housings, and in each membrane housing, which is essentially a pressure vessel, a number of membrane modules that carry out the processing. So that's a bit about membranes and membrane modules, and what I want to do now is to touch on the first application I want to mention, which is reverse osmosis to desalination. So in reverse osmosis, what we're doing is taking a salty water and we're applying pressure to it and contacting it with a membrane so that the water will pass through the membrane and the salt is held back by the membrane. This will be a classic layout for a reverse osmosis plant here. If you have seawater, you'll typically pre-treat that to remove algae, bacteria, slime, and everything else, and you'll have a dissolved solution of salt, typically 35 grams per litre of sodium chloride. You'll put that through a high-pressure pump and pump it against a reverse osmosis membrane module. Some of the water will pass through the membrane. That's the permeate with a low salt concentration, and then some of the water will be returned as a concentrated brine. Of course, this is still under pressure. And so generally, in the interest of energy efficiency, we'll try and recover the pressure energy from that recovered brine, which we'll take out here. And you can see that typically I would double the concentration of the salt from about 35 grams a litre to 70 grams a litre, which means I'm recovering about half of the feed seawater as low salinity fresh water. And of course, to do that, I use one of these spiral well membrane modules, and that spiral well membrane module is made up of a whole lot of leaves rolled around a permeate tube. If you look at the level of the individual membrane, there'll typically be a layer near the surface of the membrane where there's concentration gradients because the water is passing through the membrane. We call that concentration polarization. And at the very separating layer of the membrane, what you've got is water passing through and salts hopefully being rejected from the membrane. As I alluded to, this is a thin film composite, so we'll have a non-woven material that we use to cast an open membrane on using phase inversion, and then a traditional polyamide thin film. Now, we've done an amount of work on this under the BP-ICAM project with BP, and the reason this is interesting for the oil and gas industry is it turns out that one application of desalination is to produce fresh water, which is then used to inject into rock structures. And you can imagine that when you have oil in a rock structure, and this picture here shows you water and oil in a rock structure, then the way that the oil and the water hang on to the rock or interact with the rock is key in determining how much oil you can extract from the reservoir. So if you can make it so that the oil will more easily come out of that rock structure, you'll get a higher oil recovery. And enhanced oil recovery can be worth literally billions of dollars in an oil field. It turns out that research in BP has found out that if you use fresh water to inject down a well, to repressurize the well, then that fresh water means that the oil more readily lets go of the rock and comes up to the surface. So by injecting fresh water down an oil well, you can recover more oil. And so there's an interest in desalination of seawater for use as injection water. And if you look at the state of the art in desalination, I think the current challenges for reverse osmosis desalination, very simply put, are here. So one thing people are looking at is higher permeance membranes. In other words, getting more flow through a given membrane area. Now, there's some confusion around this because some people think that if they have higher permeance membranes, it's going to reduce the amount of energy that we need for desalination. There's a very good paper in Science from the Elimelech group at Yale which points out that isn't going to happen. So the amount of energy that we need to desalinate water has gone down for the last 3 decades from up over 15 kilowatt hours per meter cubed down to around 2 kilowatt hours per meter cubed. The theoretical minimum amount of energy you need for water desalination will depend on the amount of water you recover and the starting salt concentration in the water. But as a midpoint, the theoretical minimum amount of energy you'll need is a bit over 1 kilowatt hour per meter cubed. So actually, we're just under 2 now. We're quite close already to the theoretical minimum amount of energy we need. So the real reason that we might be interested in higher permeance membranes is because we'll need less membrane area for a given installation. And if we need less membrane area, and we're working in an offshore environment, for example, to produce water for re-injection, then the weight or the size of the membrane plant can be very important in its overall cost effectiveness. A couple of other key considerations in reverse osmosis currently are how we go about producing low fouling membranes. Eventually, reverse osmosis membranes foul with biomass or scale, how we can produce chemically resistant membranes that we could more readily clean or sterilize, and also how we can produce modules with lower pressure drops and high mass transfer. I'll come back to that at the very end of my talk. But one way of trying to develop better membranes, of course, is to understand how the membranes we have work. And in the next few slides, I'm going to be talking about thin film composite membranes made by this multiple step process that I talked about before. So there's going to be a support layer and then a thin film layer on top of the membrane where the separation is affected. Now the interesting thing is when you look at these membranes, and I've showed you a diagram that shows them more or less as flat sheets on top of support. When you look at these membranes under electron microscope or using atomic force microscopy, so you can see here on the left atomic force microscopy, in the middle we have SEMs, they're not flat. So they actually turn out to very complex morphologies. So if you look down at the surface of one of these membranes, it's actually got all sorts of things sticking out the top of it. And if you look at the rear side, the back side of where the film is, that's much smoother. Under the SEM here, you can see we have all sorts of ridges. And in fact, this is called a ridge and valley structure. So this structure isn't what you think it's going to be before you look at it. You think you're going to get a nice flat polyamide film through which permeation occurs. And what you really have is a polysulfone layer on top of a polyester support. This is an SW30HR membrane, which is a membrane made by Dow Filmtech. And what you can see here is we have this very complicated structure. And the question is, how does that structure impact on how we do reverse osmosis and how reverse osmosis performs. So a key thing in figuring that out is to try and understand that structure. And with colleagues in the materials department, we've worked on using focused ion beam milling to chop sections of one of these top layers of these membranes, reverse osmosis membranes, to go through it and cut sections out of it, then to analyze each of those sections under a high resolution SEM, and then by using tomography to reconstruct those slices and come up with a picture of what the envelope of that membrane looks like. So you can see, as you saw in the SEM, that we can now get a physical representation of this membrane in terms of the structure and the morphology on the top layer and on the back side of the membrane. And obviously we're interested in a bit more detail in that, so what we can do for each of those slices is look in each cross-section how the surface of the membrane looks. And I think there's one word for that, which is it's complex. So the membrane looks quite complicated. So how do we go about trying to describe how we get transport through a membrane where you've clearly got different layers, you've got these leaves, you've got protuberances sticking out, and so on. So the way we have approached that problem is to make our own membranes, because the commercial suppliers of membranes, for very sensible reasons, generally won't tell you exactly how they make their membranes. They're commercial secrets. So you know they make a membrane, you know that it works for reverse osmosis, and you can study it by doing electron microscopy and so on. But if you want to try and change the chemistry, you can't really do that. You don't know how they've made it. So we decided to make our own membranes. And one of the challenges was how we would manipulate the morphology of that membrane. And what we did in order to do that was to take a rather unusual fabrication technique, which was known in literature but not widely used, and that was to make cadmium hydroxide nanostrands. And we use these in a layer here, so we filter a very smooth, flat layer of cadmium hydroxide nanostrands on top of an open ultrafiltration support. And we soak this layer here with an aqueous solution of amines. And then we contact that with a hexane solution of trimethyl chloride, and we get a polymer nanofilm forming at that interface. So if you look here, you can see that this nanostrand layer is very, very flat. That's 120 nanometers, and this forms a very flat layer on which we can form membranes. So it acts as a reservoir for aqueous MPD. It allows us to fabricate freestanding polyamide layers, and then we can move those onto different substrates. Well, what we found when we did this is that if we use a low concentration of amine and trimethyl chloride, we can get extremely flat, very flat films made of polyamide. As we increase the concentration of the reactants, we get these rugose structures, the crumpled layers that you typically see in the commercial RO membranes. And we think that's because as this interfacial reaction is happening, it's releasing heat. And that heat is creating instabilities and buoyancy effects at the interface, and those are essentially frozen at the time of the reaction when you form this film, interfacial film. But we use this technique to make flat films and take them off supports. And we could then analyze those films. For example, now we could start to look at the thickness of the polyamide layer. And what you can see here is one of these very thin films laid onto a silicon wafer, and we've dragged an AFM tip across the lip of that film. And what you can see is you drag the tip across, it jumps up by about 8 nanometers. And that tells us that the thickness of that nanofilm is about 8 nanometers. Up to now, people have stated that the thickness of reverse osmosis membrane thin films are in the region 50 to 100 nanometers. And what they're really measuring is top to bottom thickness of that rugose rough layer. But what we think the membranes comprise is these very thin films that then crumple up. So the real thickness of the separating layer is less than 10 nanometers. The surprising thing with these films is that actually they're very strong. So you can see here we made a lasso, which is about 1.5 centimeters in diameter, and then we attached one of these 8 nanometer films to the lasso. So if you just think about that for a minute, you've got an aspect ratio of something like 1,000,000 here, 1 times 10 to the 6, because you've got a film which is less than 10 nanometers, which is more than 1.5 centimeters in diameter. So it's about 20 molecules thick. And another surprising thing about that film is that it's very strong. So that if you laid the film on the lab bench and got a pipette and you sucked it up a pipette, which is what we're doing on the right-hand side here, the film doesn't break. You can suck it up the pipette, get it out, and spread it out again. So it's very thin, it's very flexible, and it's very strong. And that's what goes on the top of these reverse osmosis membranes. So we can use that for all sorts of interesting experiments. And what I want to do is just touch on one of the experiments we've done around fouling. So you can see here a fouled membrane module. This is all gunged up at the end of the spiral wound membrane with grey sludge and scale and so on. And what we've done is tried to imitate this fouling with a defined model system. You can see one of our membranes here where we've been filtering BSA, which is a protein typically used as a model foulant. And so the question we can ask is, what is the effect of the roughness of the membrane on fouling? So I can make a very smooth membrane, I can make a very rough membrane. What is the effect on fouling? Now, when you think about that, you probably will think that the rougher the membrane, the more easily it's going to foul. And in fact, that is the received wisdom. That's what people have claimed, that's what people think, that a smooth surface will foul less. So we can imagine you've got a rough surface here, and this is a cartoon of one of those rough, crumpled up films that I showed you. So it has the peak and valley structure, and then as we apply cross flow across the membrane, the permeate flow will be down to the surface of the membrane, and that will tend to carry the foulants down into the membrane. If we have a flat membrane, then we'll have cross flow going across the membrane, and the permeate will go down into the membrane. But you can see that if the foulant on the surface of the membrane, the smooth membrane, then we would expect that we'll have less fouling. And in fact, if I show you a couple of results from that, so on the left we have a smooth membrane that we've made on these cadmium hydroxide nanostrands, and on the right we have a membrane with a roughness of 86 nanometers. So if you look at that side on, the effective thickness looks like about 86 nanometers, but actually it's a whole lot of films crumpled up that are probably only about 8 nanometers thick each. And if you take one of those smooth polyamide films on a polysulfone support and compare its performance in fouling to a rough polyamide film on polysulfone supports, here's what you find. So you can see that in the smooth membrane you have some foulant. This is BSA building up here, but you have large areas of pristine membrane where we don't get much fouling at all. And under the electron microscope, you can see here there's really an insignificant fouling layer. If you compare that to the rough layer, so here we have a rough polyamide film on top of a polysulfone support, we have much less pristine membrane, we have a lot more foulant building up, and we get something like a 5 micron fouling layer. So looking at that data, you think it's clear that the roughness of the membrane is leading to more fouling of the membrane. It's not quite as simple as that. When you look at the permeance, or the flux of the membrane, it turns out that the rough membrane has a permeance of double or more the smooth membrane. And I'll come back to that shortly when I get on to organic solvents. So it has a higher permeance. So it turns out that the membrane, which appears to be 90 nanometers thick, has a much higher permeance than the one which is 8 nanometers thick, and the reduction in flux that you get is higher for the membrane which is rougher. So you get 12% flux reduction. This is normalized flux on the right versus 7% flux reduction on the smooth film. The thing is, that's not a well-controlled experiment because you've got two things that are different: the roughness of the membrane and the permeance of the membrane. And the higher the permeance, the more rapidly the foulant is brought down to the surface of the membrane. But with this platform technology we've developed of making these very thin or rough or smooth films and putting them on supports, we can actually put this film on different supports. And the support can affect the permeance of the membrane. So what you see here is two different supports: polysulfone on the left and the cross-linked polyamide on the right. And this support gives you a much lower permeance. So what we did now is we made rough membranes on both of them. So both of these are rough membranes, but the rough membrane made on the polyamide support, the cross XP84, these blue points, is of the same order of permeance as the smooth polyamide. So now we can compare the membranes which have the same permeance, the black and the blue points, which are rough and smooth. And what you can see when you look at the data here is they lose about the same amount of permeance. So the rough membrane and the smooth membrane both go down about 7% in fouling when you expose them to the BSA. And in fact, with the rough polyamide, which has the same permeance, you can see there's quite a lot of pristine membrane, and there's an insignificant fouling layer on both the smooth membrane and the rough membrane. So that tells us that actually, if you control the experiment by using these thin films and playing around with the supports, there's actually no effect of roughness on fouling at equal permeance. So counter to what we've believed up till now, the roughness of the membrane doesn't impact on the fouling. More important is the permeance that the membrane has and the rate at which the foulant is brought to the surface of the membrane. So the second application application of membranes I wanted to talk about in molecular separations is nanofiltration in organic liquids. And this is something which, as I mentioned at the start of the talk, my own research group has worked on for the last decade or so. And it's an interesting one because if you think about water processing and desalination, reverse osmosis has come to dominate the market for water desalination over multiple effect evaporation. And the reason for that we've already been through with me sitting on my bicycles. It's just because evaporation cannot compete on energy with desalination by membranes. So this is a picture of a modern desalination plant. They handle 100,000, 300,000 meters cubed per day, so large flows. But if you look at the same equivalent volume processing plant for organic liquids, for example, an oil refinery, all you can see is distillation columns. So membranes haven't made anything like the inroads into distillation and to organic liquids processing that they have into water processing. So the question is, can membranes produce the same paradigm change for organic liquids processing as they have for water? And the answer is maybe in some cases. And I'll start off by giving the example of the largest organic liquids filtration plant ever built so far. And this is used for dewaxing of lube oils. And this was invented by W.R. Grace, and they made the membranes and installed by Mobil, then became ExxonMobil. Now, the idea here is you have a waxy feed, which is a mixture of oil. These are high molecular weight molecules, and MEK and toluene as solvents. And you chill that down, and the wax precipitates out as a white, waxy material, which you take out in these dewaxing filters, and the slack wax goes off to recovery. And then coming through at something like minus 10 degrees C, you'll have your filtrate off to oil recovery, which is high molecular weight oils and solvents. And what you have to do with these is to heat them all the way back up to the boiling point of the solvents, to recover the solvents and put them back in here. Energetically, that's not sensible because you have to refrigerate the solvent, then you've got to heat it up to evaporate it. So what they did was come up with a process where they could do the separation of a large quantity of the solvent at low temperature. So when it comes through the filter at minus 10 degrees C, apply a membrane. If that membrane is stable in MEK and toluene, you can recycle the solvent back around into the system and add it in after the refrigerator, drastically reducing the load on your refrigeration plant. So they came up with what I call the first generation of organic solvent nanofiltration membranes. These are stable in solvents like toluene, heptane, ethyl acetate, and they're membranes made from polyamides. And W.R. Grace and ExxonMobil worked together to build a plant at their Beaumont, Texas refinery. This is a shot of the plant here. So you can see it's a whole lot of insulated pipes. Those pipes are housings I alluded to earlier. So in each of those pipes, you've probably got 4 or 5 spiral well membrane modules put together in a string. And they're operating with a solvent mixture. And that can handle up to 11,000 meters cubed per day of solvent. It cost $6 million to build in 2000, and the net benefit was $6 million per annum. So it had a 1-year payback. Just to give you an indication of the performance of that plant, this is data for a period of over a year on the commercial production of lube oil. And what you've got on the top plot is the permeate rate in cubic meters per hour. You can see that goes down. And that's one of the problems with membrane. As the flux goes down over time, that can be due to fouling on the surface or aging of the membrane. And what you can see here is the oil content. So going in, the oil content is typically 18 to 22 weight percent, and coming out, the oil content is always less than 1 weight percent. So the oil that you're recycling back around, the solvent you're recycling back around, is essentially clean, and you're rejecting 95 to 99% of the oil. But the trouble with those membranes in terms of using them more widely outside of refinery applications is they're not very chemically resistant. So in fact, that polymer, P84, that was used to make those membranes is the polymer I showed you in the video of how we make membranes. So it's clear that that polymer will dissolve in solvents like DMF, and that's how you cast it. So how are we going to make membranes that are more generally stable across all sorts of solvents and different chemical regimes? Well, you might think about using a very chemically resistant polymer, for example, Kevlar, which is a type of polyaramide, or PEEK. These are stable in many organic solvents. The trouble with using those polymers is you can't dissolve them. And if you can't dissolve them, it's extremely difficult to cast them as membranes. So you have to think of another way of making them into a membrane. A second strategy for making membranes would be to take something like the polymer I showed you, the polyamide, cast it, and then after you've cast it, cross-link it, so that the polymer becomes, instead of being a series of chains, becomes chains that are linked together by other smaller molecules, cross-linking molecules. And that should make them insoluble. So that's a strategy that we followed. And what we found is that if you take a membrane and you cast it, this is from P84 polyamide, if you put it back into DMF as a solvent, in less than a minute, the membrane is totally redissolved here. But if we chemically cross-link that, and we did this using diamines to break open the polyamide ring, then after 2 years, the membrane is still stable. So by casting a membrane and then cross-linking it, you can make it stable to even the solvent in which you originally dissolved the polymer. So that developed its own story. The original membranes made from polyamide were made by Grace with this Maxley wax plant. And in my research group, we came up with the idea of cross-linking these polyamide membranes. Actually, as it turns out, we patented that idea. We granted patents for it in various jurisdictions. And then we decided that we would start to manufacture those membranes. So we had a company that came out of Imperial College, Membrane Extraction Technology. We developed a process for making these membranes, dissolving the polymer, casting the membrane, cross-linking them chemically, all of this at larger scale, drying the membrane, making these spiral wound membrane elements, and then finally using quality control on them. Many of our customers actually were in the pharmaceutical industry, and so we had to have a cartridge, a spiral wound cartridge. Of course, all of the components had to be solvent stable, and the cartridge had to be leak free. Importantly, we also had to meet regulatory requirements for pharmaceutical applications. And we managed to do all of that. Our first commercial installations of this membrane, which we trademarked the Duramem membrane, were in pharmaceutical factories. You can see one here at a GlaxoSmithKline factory in Cumbria. And around 2010, that business, MET, was acquired by Evonik, which is a large German chemical company. And Evonik built a larger facility in West London where they currently manufacture spiral wound membrane modules up to 8 inches in diameter, so large-scale spiral wound membrane modules for organic solvent nanofiltration. So that's the story of the cross-linked polyamide, which has a number of applications. But the question is, what are the challenges for molecular separations in organic liquids now? And I think some of the interesting points are, how do I get better chemical stability? How do I improve the permeance? How do I get rid of aging of the membrane? And how do I improve the separation accuracy? There's also some questions around the system engineering. Can I model the transport through the membranes better? Can I get more accurate separations? How do I do process simulation and modeling? How do I get over concentration, polarization, and module design? And I think it's fair to say that some of these questions have received a lot of attention: chemical stability, the permeance, the transport modeling, and some of them have received a lot less attention. And I'll come back and make some comments on that at the end of my talk. But I want to return to these 10 nanometer polyamide films that we made. So we made these because we were thinking about reverse osmosis membranes, but it turns out these are also quite interesting for working with organic solvents. And what you can see here is the rejection of a dye. This is the structure of a dye. This is the dye in the feed. If we filter this feed through the membrane, the concentration goes up in the rete intake because the dye can't pass through, and there's almost no dye in the permeate. So these very thin polyamide films have very good rejection of solute molecules. We also found that if we treat them with DMF as a solvent, it really improves their flux. So the flux typically go up by a factor of 3 or 4 from this blue line, where we test the permeance of a number of different solvents, to the red line, which is what we call activated with DMF. So these very thin polyamide films are interesting membranes for organic solvent filtration. And I promised you earlier in the talk that I'd come back to why the crumpled membranes have a higher flux than the smooth ones, or higher permeance. So what this data shows you is the permeance of acetonitrile, a solvent, through a crumpled membrane and through a smooth membrane. So you can see the crumpled membrane here and the smooth membrane here. And if you look at the surface of this crumpled membrane, it's really rough. The surface of the smooth membrane is, of course, smooth. And the reason we think that the flux is much higher through these crumpled membranes is a lot of these things that stick up here are actually hollow. So you've got a whole lot of extra area per area of membrane in the form of all these hollow protuberances and things sticking up into the fluid, and that increases the area you have available for filtration from those membranes. So the reason the crumpled membranes have a higher permeance is just because they have a higher filtration area per area of support. We didn't stop there. We got very interested in this idea of very thin nanofilm membranes, and we wondered whether we could, by changing the monomers we use for this interfacial polymerization reaction, change the pore structure inside the thin films. So we realized that these nanofilms of highly cross-linked polymer networks can achieve high fluxes through interfacial polymerization, but we started asking ourselves, could we could we design the monomers that we use for this interfacial polymerization reaction to influence the pore structure in the membrane? So to test that, we tried two what we call contorted monomers. So these are monomers like this, where they have angles that can't bend very easily, and we tried two flat monomers. So we wanted to understand whether membranes made from these flat monomers and membranes made from the contorted polymers would offer different properties. And the way we did that was to carry out an interfacial reaction again using trimethyl chloride and hexane and various contorted and non-contorted phenols in a sodium hydroxide solution. So these react together to give us a polyester or polyarylate network, and you can get the idea of what that network might look like here. Now we're lucky in our chemistry department to have Kim Jelfs, who's an expert in molecular modeling of polymeric materials, and so Kim did some modeling for us. And what she predicted from these models that she did is that using these two contorted monomers here, these are these two boxes, we would have far better interconnected pore structures than if we use these flat monomers here. So these are models made from the flat monomers, and the red signifies the pore structure and the green signifies the interconnected pores, and you can see here that the interconnected pores are much bigger when we have these contorted monomers. Even though if you look at this plot, the pore size isn't that different, the key to using these contorted monomers is that the pores are far more interconnected. And when we looked at the permeance of those membranes, we found that that was exactly what we observed experimentally. So what you can see here on this left-hand plot is the red plots for the membranes made from the contorted monomers. So the red and blue offering very high permeances, and the membranes made from the flat monomers, the green and the pink, offering very low permeance. And if you look at the rejection of these membranes versus their permeance, you can see these are the typical membranes available in the literature, and these are the two membranes we made with the contorted monomers. So by adding contorted monomers into our mix, we can get some control over the pore structure of that very thin film in the top layer of the membrane. And that came out just earlier this year in Nature Materials. So now I want to finish with a few slides on future outlook. So I think there's three key things that are important in membranes. One is their stability, and by that I mean their stability with respect to chemicals and solvents in their environment, and also their stability over time, or aging. There's their permeance, how much liquid you can get through them per unit of time, per applied pressure, and there's selectivity, so how good they are at discriminating between different molecules. I think it's fair to say that most of the work so far has really gone into the permeance, trying to make membranes with higher permeance, and then their chemical stability. But if you look at the performance limitations on the membranes, most studies are either membrane-focused or application-focused. But major limitations on performance can actually come from your system factors, for example, chemical stability, aging and fouling, but also concentration, polarization, osmotic pressure, and hydrodynamics. So if this is the membrane here, as I have a flux towards the surface of the membrane, the non-permeating species, or the solute, will build up and form what we call a concentration polarization layer here. And this eventually leads to a higher concentration of solute at the surface of the membrane than in the bulk liquid, increases the osmotic pressure, and reduces the driving force available for the process. And that's reflected in these curves here. So you can work out what effect that will have by just solving a simple equation here where you take account of the mass transfer. And what you can see is this is a parity line between the intrinsic membrane permeance, if I have a membrane and I measure its permeance in perfect conditions, versus the achieved system permeance, and this is for ethyl acetate as a solvent and a 10 weight % solution of sucrose octoacetate as a solute. So if I had an infinite mass transfer coefficient in the system, so I pump fluid over the surface of this membrane quickly enough, and I had enough turbulence at a very high mass transfer coefficient, I get a slight difference between the achieved and intrinsic permeances because of the osmotic pressure. But as my mass transfer coefficient goes to 1 times 10 to the minus 4, which by the way will be a very good mass transfer, very high, down to 1 times 10 to the minus 5, you can see that the achieved system permeance, what I get out of my membrane, starts to level out and does not increase as the intrinsic membrane permeance increases, which is to say that I can improve the permeance of my membrane, but it won't necessarily improve the permeance that I get out of the system because I'm totally limited by mass transfer in the boundary layer above the membrane. Another limiting factor is pressure drops in modules. We've already gone over spiral well modules, and what happens is you have some pressure drop down the feed flow side, and you have some pressure drop on the permeate spacer here. So that the pressure you have here will have to be greater than the pressure you have here to get flow to go down the spacer, which means you apply a pressure, but the pressure inside your permeate spacer will build up, and so the actual difference in applied pressure won't be as high as your feed pressure. And that can have a dramatic effect as you improve the membrane permeance, because as more and more material comes through the membrane, you get a higher and higher pressure drop inside this permeate spacer. So purely on pressure alone, for a pure solvent, you can see here's my parity line, and this is what I would actually get out of a typical membrane. So initially I get some increase with the system permeance because of my membrane permeance, but at some point increases in the intrinsic membrane permeance simply won't increase my achieved system permeance anymore. And if you put together concentration, polarization, and pressure drops in spiral well membranes, you get this rather dismal curve here, which shows you that if I increase my intrinsic membrane permeance, it's actually not going to do much for my achieved system permeance, which is to say that other factors than the membrane permeance are limiting the system: concentration, polarization, pressure drops in the module. And so in concluding remarks, I would say that molecular separations by membranes are well advanced in reverse osmosis, and they save massive amounts of energy over alternatives such as evaporation. So the invention of reverse osmosis technology has meant that we can recover water, fresh water, from seawater using very much less energy than if we only had evaporation available. Nanofiltration in organic solvents is still in its infancy relative to reverse osmosis. It's not nearly as well established, but I think there's also the potential for massive energy savings if we can develop ways of filtering organic liquids using membranes instead of using energy to evaporate those liquids. Understanding membrane formation and function can lead to fundamental insights which catalyze process improvements. So for example, by having a platform where I can play around with the membrane separating layer and the support independently, we've been able to show that fouling, previously thought to be a function of the roughness of the membrane, may not actually be dependent on the roughness of the membrane, but may be more affected by the permeance of the membrane. Advances in membrane permeance, which are a favorite topic for studies, there's a lot of reports of people with ever higher permeance of the membranes, I think are very interesting, but they won't be that useful without tandem developments in membrane module and membrane process design. In other words, you can increase the intrinsic membrane permeance as much as you like, but unless we're able to improve mass transfer to reduce pressure drop in the modules, our systems won't be able to use that enhanced membrane permeance. So I think the most important membrane improvements are likely to be in improving stability and chemical resistance and selectivity of the membranes. So I think for reverse osmosis, what we need is membranes that we can clean using chemicals and that we can get to be stable while we clean them with chemicals or while we apply conditions where biofilms can't develop. And I think in organic solvent systems, we need membranes with ever better selectivity so we can start to compete with the sorts of selectivity we can achieve with distillation. So just in conclusion, I'd like to acknowledge my co-workers on the BP-ICAM 10 ROMSAF project. So there's a whole team of postdocs, PhD students, academics, and BP sponsors who have developed all of that work that I showed you, and I only showed you a small amount of the work we've done on ROMSAF 10 looking at reverse osmosis membranes. I'd like to thank industrial sponsors. These include BP-ICAM as a major sponsor, GSK, Pfizer and Novartis, the EPSRC, the European Community, and then of course all members of the Livingston Research Group, past and present, who have contributed to the work that I've showed you. Thank you very much.